So welcome to the second colloquium for this fall semester. Today we have Michael Scheuerer with us. He is currently affiliated with the Cooperative Institute for Research in Environmental Sciences at CU Boulder and NOAA is also at Boulder. And he got his PhD in mathematics from University of Göttingen in 2009 under the supervision of Martin Slater. And he spent a few years at Heidelberg University before joining NOAA in 2013. Yes. Currently, he is the associate editor for Annals of Applied Statistics and monthly weather review. And today he's going to talk about some cool stuff. It's a big title, so generating calibrated ensembles of physically realistic high-resolution locations.
That was fully
You have to
That was fully
tweak that,
intentional.
yes.
To make it even harder for you.
All right. It looks much better now. Precipitation forecast flare is based on GFS model output. So,
Okay, thank you very much. Thanks for inviting me to talk here. I've been here at Mainz a few times, and it's always nice to be here. And we already gave a brief informal talk today about the hard and difficult stuff that I've done earlier, and now I retired from tough mathematics and from the theory proving business. And so this is still the most mathematical, most serious stuff that I'm doing right now, working for NOAA. But you'll find it's still mostly pictures, so it's more relaxing than this other talk this afternoon. As Suchir said, this talk is about space-time modeling of precipitation fields, and I think I should get started with giving you a crash course about how weather prediction works. First of all, how weather prediction works and what an ensemble is. So weather prediction is initially not a statistical problem. It's actually more like a physics/numerical analysis problem. So the first step is we have to figure out what the state of the atmosphere is. We do that by taking all sorts of measurements and then having some already rather complex interpolation routine to interpolate from like all these measurements that we take to everywhere in the atmosphere, because we have to know everything, and from there we can then move forward in time. Like physics tells us how things evolve by establishing physical relations that take the form of a huge system of rather complex partial differential equations. And weather prediction is basically solving a simplified version of these partial differential equations forward in time, and that tells us how things like temperature, moisture, pressure, winds, and such evolves in the future. And now, one of the difficult things about these partial differential equations is that this is a chaotic system, and that means the further we move forward in time, the faster errors grow. That means even if we had a pretty good idea of what the state of the atmosphere is right now, which we don't, because we only have a few measurements at the surface, and we would have to know it like way up in the atmosphere. So we already have only a very coarse understanding of the current state of the atmosphere, and those errors that we have even about the present state will grow rapidly in the future. And that's the reason why weather forecasts are not as accurate as we all would like to be, even though we constantly improve all aspects of the model, and there's many people working on this, but that's just the inherent difficulty of weather forecasting. And one thing that has happened in the last, say, 20 years is that people have acknowledged that there's this huge uncertainty in weather prediction, and they've said, well, then can we at least characterize that uncertainty? And that is the motivation for doing these ensembles. So instead of running a single solution of this partial differential equation, what we're now doing is that we intentionally perturb these initial conditions, which we know we didn't know exactly in the first place, so we perturb them. And also there's a lot of parameterizations of the physical model where we don't exactly know how these processes should work and what parameters we should use, so we perturb those too. And And then we just look at how the different solutions evolve over time. And that's the idea of the ensemble. So instead of one weather forecast, we get, like in this example, 11 weather forecasts. And they all differ a little bit because they were created by these perturbed initial and parameterizations. And if they still all agree pretty well, that would give us the idea that we can be relatively certain about what happens. But if they start diverging, then we know that that there's a lot of uncertainty about what's actually going to happen. And so this has been a huge step forward in weather prediction, and it's kind of the step forward into the probabilistic perception of weather as, even though the origin is deterministic but chaotic, it's useful to view this as probabilistic and just see a range of outcomes like some sort of sample of what could happen in the future. However, if we start interpreting this in a rigorous sense, then it turns out that the way we capture uncertainty is not statistically accurate. And so what that means is best explained by introducing you to one of the basic tools that we use for probabilistic verification. These are so-called reliability diagrams. And statistical reliability of forecast basically means that if we forecast that some event, say here the exceedance of 25 millimeters, which is about 1 inch of precipitation over 12 hours, if we forecast that this happens at a particular location with 40% probability, and we look at a number of cases like different days where we have always said this is going to happen with 40% probability, then on average we would like to actually see that event happen in 40% of the cases. Like that's the definition of reliability. So that means if we now calculate the relative frequency of what actually happened over a large number of cases, we would like to see this curve to be on the diagonal. Then the forecast will be reliable in a probabilistic sense. Like if we take these ensembles, say for simplicity we had 10, and then we just say, well, if 4 out of these 10 members of the ensemble were above the threshold, then we say this is a 40% chance, then this is what we get. And you see this is pretty much not reliable. And the reason for that is that, first of all, because this is such a huge system that we have to solve, and if we want to predict further in the future, we cannot even look at the single country, we always have to look at the whole globe, because the weather moves around on the whole globe. And that means that our mesh of the partial differential equation is solved is rather coarse. That means we cannot resolve the topography very well, and so there are systematic errors. And also these perturbations with which we try to represent the uncertainty, that's also a useful but not perfect representation of the true uncertainty. And for these reasons, we get these unreliable probabilistic forecasts. And that's where the statistics start. Because now what we do is that we use statistical methods to correct these forecasts, to use the output from the numerical weather prediction systems, but turn that into like a reliable probabilistic forecast, so that these probabilities that we then give for certain events to happen, that they actually keep their promise. Right? And so this is this business called statistical post-processing, which is the little niche field that I'm working on. And the idea is that we just take our forecasts, say over the last 5 years or so, and then because it was in the past, we already know what actually happens. So we take the forecast and the observations, and then we just basically try to understand in what way the forecasts were wrong, and then we correct that. So in the simplest case, you can think of this like a regression, and of course, it can be more complicated than that because a lot of variables have very weird distributions and non-linearities, but basically this is some sort of regression where the forecast tells us what the forecast thinks it does, and then we look what did the observation do, and then we correct that. That's the basic idea of post-processing. And so for precipitation, that's actually one of the nasty variables because it has all sorts of really unpleasant properties, like the fact that it is 0 with positive probability. It is spatially very intermittent, which is what we get to later, which causes lots of trouble. It is heteroscedastic, and so we came up with this regression model that tries to account for all of these things while still trying to be reasonably simple, so not to be overfitted, and so that the code is manageable for people to use them in operations. So basically, what we did is we have here distribution, which is a variant of a gamma distribution where we introduce an extra parameter where we shift it a little bit to the negative values, but then we censor it at 0, so everything that falls below 0 now is interpreted as the probability of being exactly 0, and everything above is interpreted as a continuous variable that describes the outcome of the intensity of precipitation. And then it turns out that we want a slightly nonlinear relation between the ensemble mean and what actually happens, and also it turns out that the uncertainty increases with the expectation of precipitation. So we built this all into this model. But I don't want to talk more about this because this is, at the core it's still regression, so I figured that's not interesting enough for applied math department. We're going to talk about something slightly more exciting. Here I just want to mention that if we do that, so we typically do that at every single grid point, so grid point by grid point, and for every single forecast lead time. And then we get a full probability distribution, and we can derive all sorts of probabilistic quantities from that. So that's an example from an experimental web product that we have in California. And you see here, for example, this shows the probability of exceeding 6 inches of precipitation within, I think, a week. So this was during one of the heavier atmospheric river events in California. And you see there's significant probability of exceeding 6 inches of precipitation. And again, we get there by just, our algorithm gives at every single grid point, it gives you this probability distribution, and then we just look at what's the probability to be above a certain threshold. But of course, we could also derive like quantiles and prediction intervals and all sorts of things. And for a lot of applications like this one, this is all we need to do, and we're done. But for other applications, that's not enough.
Is it still based on multiple ensembles?
This is still based on ensemble, yes. So what I didn't tell you, I went over this quickly. So this regression, we incorporate like a number of statistics of the ensemble. Like here, I just display the ensemble mean, which we use as the main predictor for the mean of this the gamma distribution. But then we also use the like a measure of dispersion of the ensemble as a predictor for the dispersion of this gamma distribution. So on the one hand, we let it systematically increase with the mean, but then also if the ensemble is very dispersed, we also say then the gamma distribution should have a larger variance, and if the ensemble was very like sharp, then we would say then we think it's a less than average uncertainty.
So the probabilities in the other plot, in the next slide, those are based on relative frequencies on ensembles?
No. This is based on that.
Okay.
So we take the ensemble, we extract all sorts of information that we think is useful, and then we fit the statistical model because we know that this direct interpretation of the ensemble does not give reliable probabilities. So, but we use that information to fit such a model, and then this is what we use for this plot. So basically, this shows you what's going on at a single grid point, and then say if we're interested in 25 millimeters, we basically just have a threshold here, and then this gives you the probability of exceeding that threshold.
So it's like finding weights using this regression, determining weights for the...
Well, it's not even weights. Like at that point, we have a full distribution.
Okay.
So we basically relate statistics of the ensemble to the parameters of the distribution. So this distribution is characterized, or we parameterize it by mean, standard deviation, and this extra shift parameter. And we set up like regression equations that link the statistics of the ensemble to these distribution parameters. And we use then a training data set of past forecasts and observations to determine like all the regression coefficients. And then once we get a new forecast, we calculate the new statistics, so we calculate the new ensemble mean, the new ensemble dispersion, and all that, and we plug that into our regression equation, and that spits us out one of these distributions, and then we have a full distribution of forecast, and we can derive probabilities of exceedance or quantiles, and that's all based off that distribution that we get by plugging our ensemble information into the regression. Okay. So, that's how we get to this map. Like grid point by grid point, we now evaluate the predictive forecast distribution. And but for applications like in hydrology, we need more than that. For drawing maps, we can look at these distributions in isolation. But like in hydrology, what we would like is that we would still like these full scenarios that we can now run through a hydrological model. And of course, we can always turn a distribution back into a sample by just some sort of sampling. And what we typically do is we take certain quantiles because we have a very small number of very small sample size. And then it's, in terms of representation, it's better to use quantiles than random sample. So here's, for a particular example, like one fixed location and 6-hour accumulation periods out to 15 days. And all different forecast lead times. This is a sample of 11 equidistant quantiles of my forecast distribution. So you see here, we expect a little precipitation or a chance of precipitation early on, then a dry period, then a period where it could rain quite heavily. And then as we go out with lead time, you see at some point it all looks the same. And that's just because our numerical weather prediction model goes off the rails. And then we know that the best thing a regression can do is just converge towards climatology. So at some point, we're just trying to reproduce the average type weather that is pretty much independent of what our model tells. Like in the beginning, our model information is very useful, and the model tells us it's either going to be very low or very high. At some point, we just converge like towards a certain climatological mean distribution. So that's what you see here as we go out in lead time, because we know past 10 days, our forecasts are just not very good. But the main point here is that now we have for every single lead time and every single location, we have the sample, but we don't know how to link them. And for some applications, that's very important. Like here, for example, we don't know how to interpret that period. Does that mean that there's going to be very heavy precipitation and we just don't know exactly when it happens? So is it just a short spike that goes up? And it could be like either one here or one here? Or does that mean that there's possibly a period of extended precipitation for a longer period, but that system might either hit or miss our basin? And so that would be like very different behavior here, and obviously have a very different hydrological response. So that's very important for stream flow prediction, but that requires now that we build a multivariate model. Like so far we just built marginal distribution, now we have to build a multivariate model. And so as statisticians, we would usually think of something like Gaussian copulars, and that's what I tried when I was still in Germany and I was still a statistician. And I got extremely frustrated because people have done this quite successfully, and actually one of our master students has done this for temperature and it works really well, but precipitation is just really, really nasty because it's not only the fact that it can be zero, you have to have like some sort of censored model, which makes inference very complicated, but then also the fact that it's non-stationary in every possible nasty way that you can imagine. And so that's why at some point I just gave up on these more like random fields models, and I just looked at, and then I came here, so I got to meet all these applied people, and I saw like how are they solving that, because like they won't use random fields anyways. Oh, here's just first, this is just to complete the motivation. So what I showed you before is like I tried to motivate dependence in time, and of course the same issue is in space. And this is illustrated here in this little cartoon that I stole from my science advisor. So if, of course, for the hydrological response, it does make a difference. If we have heavy precipitation in one basin, then further downstream that might still be fine. But if they are strongly correlated and we have heavy precipitation simultaneously in all basins, that might be a problem further downstream. That's just to say that we need to model temporal correlation, but also spatial correlation. Okay, so this is how applied people do that. It's extremely simple and effective, and the rest of the talk is how we try to make this better. So what they do is the so-called Sharkey shuffle. And their idea is as follows. We have observed weather in the past, and we have all these observations. So why don't we just take a sample of past dates, like say, if we want to know what's happened in the next 15 days, then we take the same day of the year last year and the previous year and like 11 years back, and just take the trajectories that happened in the 15 days after that date and use that as a template for the serial dependence. And that's what's depicted here. So you still see these predicted marginal distributions in the background, and then these historical trajectories, like from actual weather that happened in the past. And so here we know how we have to connect them. And so the idea is now that we just determine the rank ordering of the marginal samples of these historical trajectories, and we impose that rank order on these quantiles. And that basically means we get the same rank correlations that we learn from these past trajectories. And that's the idea of modeling dependence. And that works simultaneously in space and time, because we just reorder our quantiles. We just put like ordering labels on our quantiles based on past observations. Yes?
I can see why you'd want to do it based on the same time of year.
Yes.
Summer, winter, different, but and though wouldn't it be similar conditions be a better indication?
Yes, that's exactly where we're going to go. But bad for you that I had the idea first. But we get to that later. So yes, so that's a good point, and that's already the criticism that one can make about this. It actually has worked pretty well, and this has become for a long time the standard method that is used in hydrology. So it's working, but yes, like it's a problem that this kind of sampling is completely ad hoc and therefore unconditional. And you can see where the problems are. Like here, for example, the historic cases, they were much better. That's probably not so much of a problem because you just collapse them into like the drier conditions. The converse is a bigger concern, where here you had like a number of drier trajectories, a lot of them are down there, and now you have to blow them up to match the forecast quantiles that our forecast predicts. And one thing that you cannot see very well here, but you will see quite dramatically when we look at the spatial example, is that what also happens, and that goes back to the nasty nature of precipitation, that it can be zero. If some of your past samples are zero, you don't have any rank order. And so all you can do is that you randomly reorder, and that's a really bad idea if things are actually strongly correlated, because random reorder means you basically assume independence. So that's a really bad idea, and that's one of the bad consequences of that particular method. So here's just to complete this example. So this is these historical trajectories, and then now if we impose the order on our quantiles, then this is like the serial, like the temporal trajectories that we get and that we now use as our forecast ensemble. Like these are now 11 scenarios that describe the anticipated weather over the next 15 days, and we can feed that into the hydrological model. Okay, so here's my idea and your idea as well, but I came first. And there's a number of different ways to do that. Actually, there's several authors that have come up with variants of that. Some were basically looking for like similar atmospheric conditions. I was actually taking a more statistical or probabilistic point of view. But first what we need to do is that we have like a much larger pool of historic cases. You don't want to use everything because it still makes sense to like confine yourself to like the same month of the year, say, or at least the same season. But you start with a pool of much more cases. So here 500, okay, that's a weird number. It does not have any meaning, but it's much more than 11. And so we want to bring that down to 11. We want to make a smart selection how to bring that down to 11. And again, there's many ways to do that. And the way that I did it was basically going back to what would we like to see. And what we would like to see is that we pick a set of historical cases so that the marginal distributions of these historical cases look as similar as possible to the marginal distributions that our forecast tells us. And so if you formalize this mathematically, first you need to measure what similar marginal distributions mean. And so we have this concept of divergence. This is not the divergence that you have for vector field. That's what probability people say for when they want to measure the dissimilarity between two probability distributions. There's various ways to do that, but the most useful in that context where probability distributions are represented by a sample and we don't have densities is this integrated square difference. So we have like for two cumulative probability distributions, we take the difference, we square that, and we integrate that over the range of values. So that's how we measure similarity of distributions. And then we run this algorithm where we start with the full set, and then we basically calculate the leave one out divergences. We leave one trajectory out, and we see does the divergence get better or worse, and then we see which of the trajectories, when we leave them out, which were the worst trajectories, and then we discard them, and we go through this iteratively until we only retain a set of trajectories that has the best similarity across all the marginal distributions. That's the idea of this algorithm, and that's how it looks like. So this is the selection, again, of historic cases, but now using that algorithm instead of an ad hoc selection scheme. And you see, of course, it's not a perfect match, because there's only a finite number of cases, and we can't expect a perfect match, but it already looks much more similar to what our forecast for the next 15 days is. And so if we now do the reordering, like we have to do much less of deformation to get from the historic cases to the cases that matches our forecast marginal distributions exactly. And so I call this the minimum divergence Sharkey shuffle, because it's the same idea of reordering samples, of retaining rank ordering, and we just try to be a little smart about what we use as a template for reordering. So once I was done with that, we applied this in a case study where we had like one of these classic hydrological models that take several sub-basins of a river, and then like these models, they basically tell you how long does it take to get from one sub-basin to the other, and how much does evaporate and how much gets lost. And so this is a very low-dimensional model. It's basically for a small basin size, maybe you have on the order of 10 sub-basins, and then your temporal dimensions. So you still get to a total dimension of 400, but that's still manageable. And so that worked fine. Now, unfortunately for me, NOAA is currently moving to a new generation of hydrological forecast models, so-called distributed models, which don't just use like different sub-basins, but they use a high-resolution model, and they try to figure out like how exactly does precipitation percolate through the different areas, and what's the soil type and all that. And so, of course, now they need high-resolution inputs. So that means extra work for me. So this is the case study where I want to illustrate that problem. This area does actually cover one of the basins that NOAA is studying quite heavily, the Russian River Basin in California. And so an additional aspect that I have briefly mentioned before is that I told you that these numerical weather predictions, they come on a relatively coarse grid. And so here you see that's the size of a grid cell. That's for this model generation was 1/2 degree, so that's about 50 kilometers. And that's the resolution of the model. And so the additional challenge is that we want to bring this to a much higher resolution. We do have observations at the high resolution, like we have high resolution grid analysis, but we have to do the post-processing such that it takes us from the coarse to the high resolution. And the high resolution here, the analysis product that I'm using is a 2.5 kilometer resolution, so it's 20 times high resolution. And so in my case study now, I looked at only 4 consecutive 6-hour lead times, and like on day 3, so this is basically all the 6-hour periods that are 3 days ahead. And but now I have a few 100,000 grid points in space, and that poses an extra challenge. Here's an example that gives you an idea of how the original forecasts look. So that's the top row. This is the ensemble mean, like the mean of all these ensemble members. The bottom row, this is the analysis, like this is the truth, even though that's also just an approximation of the truth, but that's our best bet of what will actually happen. And so you see, okay, that's obviously we need some work, so that's why we're here in this business. And if we apply this first post-processing step that deals with the marginal distribution, we can of course use the coarse scale predictors and then regress that against those fine scale things. And if we take the mean, then this is what we get. You see, you already get a lot of the spatial structure out of that, but this is just the mean, and you see it's still wrong, or like wrong is a bad word, but it has quite some error, uncertainty, and so we like to address the uncertainty around that. So we like to simulate an ensemble that gives us different scenarios that represent the possible outcomes. And now you see the terrible consequences of using this original Sharky shuffle in space. Because now we have high resolution, and so we have extremely high correlations in space. And you see it's a really terrible idea to assume independence, which is the assumption implied by random reordering when you have dry conditions. And the case I picked here, it was not my intention, but it was a particularly bad case, because those 11 years in the past that I use as an example for my spatial and temporal dependence, those all happen to be really dry. So the case that I picked, that was deliberately, I picked a relatively wet case in the future because wet cases are more interesting. And it just so happened that those past 11 years were extremely dry. And so even the wettest of these cases, that's the top row here, that's the historic case, that's during the last, or basically the last 3 days, periods of this day, it had no precipitation at all. And so that means, and that's what reordered quantiles look like if we have only zeros and we reorder at random. And so, of course, that's not a particularly realistic precipitation field. so that does not work at all. So now let's use our minimum divergence Sharky shuffle, and it turns out that even that is that still needs some extra work. But first of all, it's computationally prohibitive to apply that directly in this high dimension because it's kind of costly to calculate all these divergences. So what we can do and what we have done here is that we do the post-processing not just on this fine scale, but also on the coarse grid scale of the forecast model, so on these 11 big squares here, and we just try to match this coarse scale resolution. So we upscale the analysis, and then we basically have one forecast for fine scale and for the coarse scale, and we use the coarse scale to pick our historic cases. And then for those historic cases, we still have the fine scale fields, and so we use them for reordering. And you see that already, I think I can go one further because I basically just said what this is now here. It's still the same picture. And so you see, of course, there's still areas that are dry, and where, if you look at the ranks, like this is basically the field of the ranks of these historical cases. Now the ranks are still randomized, but because we have selected them to match the distribution, what usually happens is the areas where the ranks are randomized are the areas where the forecast also says it should be dry, and so we're randomizing zeros, which doesn't matter. And so you see that these fields already look much better than what we saw before. They're still not perfect though, and that is because you see, ranks are a discrete thing, and so they like to jump. And if you look closely, that you see that wherever the rank changes, we're jumping up and down these quantiles. And so that's still a feature that's not realistic because that means we have discontinuities in the precipitation fields. We would like to get rid of that. And also what you can see here, but what you will see later in the verification that I'll show you, is that for wet situations, this deliberate selection of past cases actually makes this random reordering much better. For dry cases, unfortunately, it gets worse because now we're deliberately picking other dry historic cases, so it's very likely that everything that we selected is 0. And even though the forecast is also mostly 0, it's just by chance there could be some cases where the forecast is non-zero, and now we randomize again. So it turns out in dry situations, I mean, you can say we don't care so much about those, but then in dry situations you get, again, these noisy images. And so that's why we propose an alternative implementation where we still use this minimum divergence Schachey shuffle idea of selecting historical cases, but we apply it in a different way. So now, and that's another nice thing about this alternative implementation, we only do the post-processing at the core scale, so which is much cheaper because now we only have 11 grid points to take care of. So we only do the post-processing of the forecasts against the upscaled analysis, and then we use and when we select the historic cases, but the historic cases still come on a fine scale, and we use this fine scale to disaggregate the core scale precipitation to the fine scale. That probably sounds very complicated, but I have a series of images where I can illustrate that. So this is now a historic case that has been selected, and this is now the course, like how this historic case looks at an upscaled level. These are the forecast quantiles at the upscale level, reordered in the same way as the historic case. So here we're still just reordering, but we do that on a core scale. So you see the patterns, they match, but of course, as we saw before, we still have to adjust it a little bit. So here we make this a little bit wetter in this area, and then there's other areas that we make a little bit drier. And now we have a perfectly fine core scale field. And to get to the fine scale, we have to find an adjustment function that basically on the core scale acts to transform that field into that field, but is spatially smooth, so we can also apply this to the fine scale.
So Michael, how are you doing this upscaling?
I'll explain. Well, the upscaling, well, that's just averaging.
Or just
So I have my fine scale, and then I just look all the fine scale grid points that fall into a core scale grid point. They're just being averaged to the core scale. So okay, that's what I already said. So what we need to figure out is this spatially smooth adjustment function that I want to multiply to my historic fields, so that it adjusts the historic precipitation levels so that they match the forecast levels at each fine scale grid point exactly. And so this is shown here. So now I have my adjustment function. I still have to tell you how I get there, but like assume that I have that. This is now my fine scale historic field, and so I multiply that to that, and then I get this thing at the bottom. And because my adjustment function was smooth, now I have gotten rid of these discontinuities, and also it turns out, and that's however a little more complicated to explain why, but it also solves this issue of zeros in dry conditions. So you see, like the fields that I end up generating as my forecast fields, they kind of look like the historical case, but with a little bit of adjustment. Like here, it made it a little wetter, you made it a little drier, but it's still, because we've picked it in the way that it's similar, we have reason to assume that the structure of precipitation is still like reasonably similar, reasonably realistic. Okay, just very briefly, because I'm again talking way too much. How do we construct this adjustment function? This is for Sukir here, because he's working on very similar things, and so I just go over this briefly. So what we do is we define a number of basis functions, which I should say here are not positive definite, which is the thing that one could improve, and I'll explain later why I do that. Basically, the idea is that my adjustment function eta is a linear combination of local, like compactly supported, not positive definite, but positive functions. I want them to be positive. And so then if I just formalize what I said before, if xsi is the core scale precipitation amount at a particular grid cell, and h is my historic, like now I write this as a function, that's my historic field, and nu si is the upscaling functional that takes the historic field to the grid cell average over this particular grid cell, then what I want, and this is just again a mathematical way of writing, is like if I multiply the adjustment function to my historic field in an upscale, I want to have the precipitation amount of my already generated core scale field, because that's what I already had in the first step. So I want that condition for every core grid scale, and then if I plug in my particular functional form, that leads to that equation system. Now, had I chosen this to be positive definite radial basis functions, I could just solve this equation system. That would be the elegant way. And I hope somebody finds maybe like a similarly elegant way to actually do it that way. The reason why I didn't do it that way is that I also want to guarantee a few extra conditions. One is that if I just solve that equation system, I cannot guarantee that my coefficients are positive, and that means that my adjustment function could be negative at some spots, and that means I would be producing negative precipitation, which I don't want. So I want to constrain them to be positive, and also I want to kind of suppress volatility. Like I want this to be like, I want the differences between those coefficients not too strong, because then my adjustment function has like weird peaks, and that means through my adjustment function I'm introducing like local heavy precipitation that I don't want. I really want like smooth adjustments, but I want to retain the structure of the original field. And that's why instead of solving that equation system, I turn this into a minimization problem of just approximately solving it. And in addition, I put this penalty that basically penalizes a coefficient to be very different from its neighbors, and that just solves this by numerical optimization. So it's not very elegant. Hopefully Sutier finds a better way of doing that, more elegant way. So that's what you end up doing if you change from the statisticians camp to the weather people camp, then just do something that works. And I've already shown you that it does work. Like it does produce precipitation fields that look reasonable and have the right statistical properties. Okay.
So Michael, just one thing. If you go back one slide, so you are not putting any sort of dependent structure on these coefficients, right?
No.
So in our lattice-bit model, we want to put some sort of dependence among these alphas, so that they behave regularly rather than just.
That might be one way to do it better. I'm just trying to solve.
If that is going to improve something, but that's usually in climate that improves a lot of things.
Yeah, I'm pretty sure there's better ways of doing that. Like my objective was just, on the one hand, I want to match the prescribed precipitation amounts as close as possible. I want that function to be as smooth as possible, and I want to make sure it's positive. And that was the easiest way of getting there. If you find a better way, again, I would love to see it. I like elegant solutions, but I'm only paid for making things work, not for making things work beautifully. Okay, so how do we? Okay, so now I've shown you.
Why do you want the correction function to be so smooth? Could there be, say, topographic reasons for it?
Yes, but that should already be taken care of, like through this univariate post-processing, because I'm regressing against actually observed precipitation. I should already have taken that into account.
Are you smoothing that out somehow in the process?
No, because so let's go back to this adjustment. So all these topographic things, they're already in this historic field. So that's where I get the structure, and so the point is I want to mess with that structure as little as possible. That's why I want it to be smooth. So I still need to change them a little bit because they don't reflect exactly my marginal forecast distribution, so I have to adjust them. But I would like that adjustment to not introduce, like I wouldn't like to introduce like some strong bumps in precipitation that are only an artifact of the adjustment function and not of my actually observed historical field. So that's why I would like the adjustment function to be smooth, but at the same time it can be perfectly smooth because I will have to adjust in different regions. In some region I might have to reduce the precipitation, in another I might have to increase it, and so it can't be perfectly smooth, but I would like to find a good compromise. And again, my compromise is mathematically ugly, but it's a difficult trade-off. Okay, so So how can we more systematically say if what I did there is actually better? I mean, if you look at this really noisy field, you probably all agree that that's terrible. But is there a more systematic way of verifying that? And then again, I'm in this business like in between applied people and rigorous people, in that the rigorous people have really good metrics, which however are very unintuitive, and so it's not good if you talk to applied people who you have to convince to use my method. And then applied people have things that are very visual and intuitive, but sometimes they are wrong. Like in the sense that, wrong in the sense that they don't guarantee statistical properties like the best forecast in a certain sense gives you the best score. And so like I tried to come up with something like some diagnostic tool, and that's just pulling together different ideas that existed and just make it work in that case. So something that's intuitive, but at the same time is like rigorous. And so what I do, and this is what's often done, is first I do some thresholding. So that allows me to study heavy precipitation and light precipitation separately. And so I look at exceedance of a certain threshold again, and that just turns every field into a binary field. So that's just everything that's above 25 millimeters is black, is 1, the rest is 0. Okay, so here's my 11-member post-processed minimum divergence Sharky shuffle spatial disaggregation ensemble like 11 members. Here's the analyzed field, and so the idea is that I want to check in some way if that ensemble represents the uncertainty about the truth in an adequate way. And one quantity which I felt was reasonable based on the binary fields is I was calculating the fraction of grid points above that threshold. So you see that some of the forecasts say it's going to be completely dry, some think it's very wet. But the idea is if that 11-member sample is a good representation of the uncertainty, then if I calculate all the fractions of threshold exceedance and I calculate the rank, then the rank of the analyzed among the whole set of 12 cases should have a uniform distribution. So if I do that for all my cases, I should have a uniform distribution of the analyzed rank among the ranks 1 to 12. And I can easily check that with histograms. And so ideally the histogram would be flat. If it's not flat, then I have systematic departures, and that would then mean that my ensemble doesn't represent that fraction adequately, as I would expect it to be in that case here. So you can probably think that, so this is this noisy threshold exceedance example, and so in the mean that might actually still be right, but now, but the problem is, because of that randomization, if I take the fraction, all these fractions are going to be very similar. So it's very likely, if they're not exactly right, that the analyzed fraction of threshold exceedance either has the highest or the lowest rank, because it's very easy to be bigger than everything or smaller than everything if all these members are almost the same. And so here's these histograms. And so you see that's pretty much not uniform, especially at the lower end. You see that I very often have rank 1, and that's basically because there are many cases where the observation was 0, but if I completely randomize, there's a high chance that at least one of these grid points is non-zero, and so this very often has the lowest rank. So that just confirms what we already knew, that this method is not working very well. But here we see, and that we didn't see before, that this reordering implementation of the MDSS, it works pretty well for higher thresholds, but in the dry conditions it makes things even worse. Whereas this disaggregation implementation gives uniform histograms everywhere, and so that would suggest that at least on that particular metric, we're actually improving things, and our presentation is pretty good. I'm running out of time here, so I'll skip over the second verification metric, in which I look at subgrid scale maxima. That basically just reiterates the same thing, that now I have a quantitative score, and the standard Sharky shuffle methods give scores that are somewhat intermediate, And at the higher threshold, both of the minimum aversions methods give pretty good score, but at the lowest threshold, that one gives actually like really terrible scores. So just to leave at least a little bit of time for questions, I'll leave you with a summary. Basically try to motivate why you need to worry about space-time dependence for precipitation fields. And I showed you a few algorithms that take like an idea that people in practice have used and tries to improve it in certain ways that like addresses some of the shortcomings of this method. And so far it seems to work pretty well. There's still a few challenges. That's why we just hired another person that takes over for me and tries to fix these issues while I'm assuming new responsibilities. Okay, thanks for listening.